Hi and welcome back to McClutchy Maths. My name is Natalie McClutchy and today we are looking at some applications of index laws by looking at scientific notation, and this is our 8th video in the index law series, so let's get straight into it. Now you might be wondering, what is scientific notation? Well, we've already seen in our previous videos that we can use positive powers to represent some very big numbers. For example, 10 to the power of 7 is actually the number 10 million. That's a 1 with 7 zeros afterwards. Now, writing 10 to the power of 7 is a much neater way of writing that. So that's a way we can represent very big numbers. And we can also represent some very small numbers. And we looked at that in our previous video when we looked at negative powers. For example, 10 to the power of negative 5 is 1 over 10 to the power of 5, or 1/100,000th. So that's a very small number as well. Now, as we would express this as a decimal as 0.00001. Okay, so very big numbers, very small numbers. Now in science, we often deal with some really big numbers and some really small numbers, and we need a way to write those in much simpler form. And this is one of the reasons for this, is that science deals with a lot of extreme values. For example, if you think about a light year. Now, I'm not even going to try and say that number. I think it's in trillions of kilometres, but it's a very, very big number. And if we think about atoms, the diameter of an atom is much, much, much smaller than a millimetre. Very, very tiny indeed. So we need a way to be able to effectively express really big numbers and really small numbers without having to write every one of those digits out. Scientific notation gives us that way of simplifying really big and really small numbers. So let's talk about it first with some really big numbers and how it works. So first of all, we need to think of expressing numbers. Instead of writing out 15 digits, we can simplify that by expressing things as a multiple of a power of 10. Now, our decimal system is based on tens. So every movement that we move our decimal point, so whenever we move a decimal point to the right, it's the equivalent of raising a power. Now, we saw that in our last video when we looked at negative indices. That might be worth going back and having a look at if you haven't looked at it yet. And we built up this pattern that every time we move that decimal point to the right, it was like multiplying the number by 10. And then we move it to the right again and we multiply by 10 again. We're raising it by a single power. So here's a little example. When we go from 10 to 100, it's the same as going from 10 to the power of 1 to 10 times 10, which makes 100, 10 to the power of 2. So let's start with our first worked example. We're actually going to take that distance that light travels in 1 year, 9 trillion kilometres, and we are going to turn that into a number in scientific notation. Now, obviously, if you wanted to travel that distance, you would need to have the precise amount that you would need to actually travel. So for example, if you were sending a spaceship somewhere that was 1 light year away, you would want it to land in the right spot. So you'd need this kind of precision. However, when you're just simply talking about it from one person to the next person, or wanting to write it in a textbook or something like that, we really don't need to know that level of precision right down to the kilometre. And that's where we're going to use scientific notation. So in scientific notation, we would actually write this as 9.46 multiplied by 10 to the power of 12. Now you might be wondering, where did I get the 10 to the power of 12 from? We can see where this 9.46 comes from. It comes from the beginning here. And effectively what we've done is we've chopped off all of those other digits and said they are no longer important. We're just wanting a rough estimate. So let's have a look at how we do this. First of all, you've got to write your decimal point in to get this final answer to 9.46 times 10 to the power of 12. So our decimal point is after every whole number. And obviously if it's all zeros all the way back here, then there is no other numbers there. So we typically just write it as a whole number. But to do scientific notation, we're working with moving our decimal point. Now we talked about just earlier in this video about how when we move our decimal point to the right, we are making that number bigger. We're raising it by a power. But what we're doing here, you'll notice this is 9 trillion, but here we've actually got 9.46. So we're actually going to be moving our decimal point to the left to make a big number into a nice, small, tidy number. Okay, so moving it to the left, every time we move it, it's like we've raised it a power. So let's start, and we're going to count all the way across from our decimal point on the right-hand side over here. We're going to count all the way across to here. Now, when we write in scientific notation, it's convention that we only have one value here, and the amount of numbers afterwards depends on your question. We'll talk a bit more about that later, but we're going to move our decimal point all the way to the left until we get just after the 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We've moved that decimal point 12 places, and that gives us 9.46 times 10 to the power of 12, because every time we move that decimal point, we're raising it by a power. Okay, so that's our simpler way of writing that. Now, we moved it to the left 12 times, so you'll notice that 12, it will keep moving until we get to one digit remaining. That's that 9, and then the decimal point plops straight after that. You'll notice that the number of moves that we made to the left matches our power now, because we've effectively raised the number 9.46 to the power of 10 times 10 to the power of 12. 12 moves of the decimal place makes 12 more additions to the index. Okay, so our new answer, you'll notice, is not 9.46073047250, because the whole point of doing scientific notation is we want to keep it simpler. So that would not be simpler. It would take no time, no extra time saving by writing it that way, and it would be no easier to read. So we're actually effectively chopping off, as I mentioned earlier, after the 6, and it's a form of rounding. So that's something to bear in mind. Scientific notation is a type of rounding. So that means we're going to follow all our normal rounding rules. So, for example, if I decided to chop off here after the 0 and have this would become 9.461 because I have to look at that 0 and then I look exactly to the right. This 7 tells me I've got to round that up to a 1. So if I had to use this part here as 9.46 and 1 more decimal place is what the question's asking of me, it would become 9.461. So once again, those rounding rules apply. However, it is convention and what I mean by convention, it's tradition, or it's typical in maths for us to usually round there to 2 decimal places. Sometimes your teachers may prefer 1 decimal place or even no decimal places at all. So you need to read your question very carefully or ask questions if need be. If you're asked to round this to 1 decimal place, this 4 would round up to 5. So it would be 9.5 times 10 to the power of 12. Okay, so just be aware of the level of rounding that you have to do. So we're just basically chopping off all those digits and saying they are no longer relevant. We just want to keep this to 9.46, and then everything else after this means we're rounding roughly to 9.46 trillion kilometres. Like I said earlier, that's not so important if you're just wanting to talk about in a textbook or on a PowerPoint or in a lecture the rough distance, because the reality is no one's actually ever travelled a light year yet. However, if we were to do that one day in a spacecraft, we would definitely want the level of precision right down, in fact, to the nearest metre to make sure we made the landing correctly. However, rounding is a useful way of communicating ideas, and that's what we're talking about today with scientific notation. Let's look at really small numbers now. This is the size or the diameter of an atom, although atoms do vary in size. This is just one type of atom, and it's very, very small, as we can see, much, much smaller than a millimetre. Okay, so we're going to be expressing this in scientific notation. So once again, it's going to be a value multiplied by a 10 to a power. However, in this case, it's going to be a negative power because it's a very small number. So this time we're actually going to be moving, instead of our decimal place to the left, we're going to move our decimal place to the right. So here's our decimal place here. We're actually going to be jumping it all the way across until it goes after our very first digit. Because as you remember, I mentioned earlier with scientific notation, we only have one number to the left of the decimal point when we're finished. So let's count our moves over to the right. So we've got 1, 2, 3, 4, 5, 6, 7, and now our decimal point is now after the 1, which is where we wanted it to get to. So to write this, I've moved that decimal point 7 times. I have to remember how many times I moved it. So now it would be 1.0 times 10 to the power of negative 7. I could also write that as simply 1 times 10 to the power of negative 7 as well, because if there's nothing after the decimal place, then we don't even have to write that 0 there at all. Okay, so we can see that that's a very, very small number. 10 to the power of negative 7, we're talking in the tens of millions. It's 1/10 of a million, smaller than a millimetre. That is teeny tiny. Okay, now this might be the slide you want to take a photograph of, or maybe screenshot this one. This is a recap, and this is what you've basically got to memorise. So with really big numbers, our decimal point is moving to the left. With really small numbers, decimal point goes in the opposite direction. With a big number, your power is positive, and with a small number, your power is going to be negative. A good way to remember this is to think of a number line. On a number line, all the positive numbers going into infinity make really big numbers, but our really small numbers are all our negative numbers. So that's a good way to remember it. So here's an example here, going from 4.5 million goes down to 4.58 times 10 to the 6. This is how it could look. Or going from a really small number here to 3.2 times 10 to the power of minus 4. Now you'll notice that when it's in scientific notation, both of these look very similar. The only difference in that final result is that 6 and that negative 4. So this tells us here that we're looking at a very big number and that we're looking at a very small number. So being able to read the scientific notation and know what it's talking about is also an important skill. So make sure you memorize this slide. Okay, let's do a couple of very quick worked examples, and then that'll be time for us to go. So first of all, we're going to write now numbers that are already in scientific notation as basic numbers. What that means is take it out of scientific notation back to a big number again. So I've got a little strategy for this. Your teacher may have a slightly different strategy, but I find this one easy to remember. Firstly, I've got this power of 5. Okay, so that means that my decimal place has been moved to 5 positions over. I've got to move it back basically to get back to that basic number. So what I'm going to do in order to do that is I'm going to just simply add 5 zeros to the end of 2.93. I'm not going to need all of those zeros, but adding those 5 on there gives me somewhere to move my decimal place to. If you just simply try and move that decimal place into thin air, it gets very easy to lose your spot and forget how many zeros to add on. So I always start by changing that to 2.93 with 5 zeros on the end. Now we're going to move that decimal point to the right. And we're going to do it 5 times. So let's see how it goes there. We've got 1, 2, 3, 4, 5 positions there. So my new number will now be 293 with 3 zeros, dot 00. Now I actually don't need these 2 numbers on the end, because remember, any zeros after the decimal place, if there's no other numbers with them, you can just chuck them out. They don't need to be expressed at all. It's simply 293,000 is our final answer, and that's can be checked again. If you're wanting to check your answers in an exam, just pop that decimal place back on the end and go back 5 spaces, 3, 4, 5. Do you get to the same spot? That's a good way to check your work, is to do things in reverse. That's worked example 3. Let's look at worked example 4. We're going to take this. We know it's a very small number because it's got a negative power. And this is something like a little reality check to do at the very beginning, just to make sure you're moving in the right direction. Okay, so you know if it's a small number, it's going to be 0.00 something. Okay, so the way we do this one is, instead of adding zeros to the end of the 76, we're going to add them to the front, because it's going to be 0. something 76 is where we're going to end up. Okay, so let's add those on the front. Now, normally, if I had the number 7.6 and I had zeros in front, those zeros would just disappear. But this time we're actually going to move that decimal place across to the left. Okay, 3 places. So starting where it is now, 1, 2, 3. And that means my decimal point is now going to go in there, 0.0076, a very small number. Now, it's always important to remember that any number that we write can only have one decimal point. What I often see students doing is leaving that little dot on the end in an exam. So what I would remember to do is just to rewrite your answer at the very end without that original dot there. So start with just 0.0076, final answer, or put a circle around your final answer with only one decimal point. Did you mean to make a big number or did you mean to make a small number? Have a look at that power at the very beginning. What should you have made? If you've ended up with the number 76,000, then, which is a common mistake people make, they've moved the decimal place the wrong way. So if you go and end up doing that, just do that logic check at the end. Should I have made a big number or a small number? And use that little memory tool that I suggested. Negative numbers mean small numbers because they're below 0. Well, did you find this video helpful today? I sure hope so. And if you did, there are some ways that you can engage further with the channel. Firstly, you could like and subscribe and hit that notification bell so you'll always know when our next video is available, and you can follow us on Facebook and on Instagram. You can also tell us in the comments as well. It's always lovely to hear from you. And if you've got any questions at all, mcclatchymaths@yahoo.com is the place to reach us. Thank you so much for watching us today. I'm Natalie McClatchy. Have a wonderful day.